Talia, Talia. Okay. Uh, Good evening, everyone. Yeah, actually, this is a historic moment for me to do this welcome address because I'm welcoming my batchmate, the resource person for this evening, Professor Janta Kodikare. Yeah, this event is proudly organized by the Civil Engineering Sectional Committee of the ISL, and it is my great pleasure and privilege to deliver these opening remarks and extend a very warm welcome to all of you joining us this evening, organized as part of the knowledge sharing session of the Civil Engineering Sectional Committee. First and foremost, I extend a special welcome to our esteemed resource person for today's session, Engineer Professor Jayanta Kodikara, who will be sharing his expertise on the highly relevant and fascinating topic frontiers in geotechnical engineering, climate resilience, and digitalization. The mere reason this topic is timely in Sri Lanka is that the widespread devastation caused by Cyclone Ditwa and its aftermath provides a stark illustration of climate driven risks to geotechnical and transport infrastructure. Let me briefly introduce our distinguished speaker, Professor Jayanta Kodikara, in this forum. He is a graduate of the University of Peradeniya and holds a PhD from Monash University, Australia. He is the director of ARC Hub for Smart Next Generation Transport Pavements, SPARK, within Monash Civil Engineering. He is also the leader of Monash Pipeline Research Group, which has led to multi-million-dollar global projects, including the Advanced Condition Assessment and Pipe Failure Prediction Project and CRCP Smart Lining for Deteriorated Pipe Rehabilitation Project that resulted in the development of Monash Pipe Evaluation Platform hosted by WSAA. He has over 500 publications on a diverse range of topics and graduated about 50 PhD students. He's a chartered professional engineer in Australia and a fellow of Engineers Australia. His fundamental research has led to the development of the MPK, that means Monash Peradeniya Kodikar framework, and model for unsaturated compacted soil modeling, which uncovered the direct link between the traditional compaction curve and advanced unsaturated soil modeling. Seminal contributions in applied research include elucidating the mechanisms of varied water pipe failure and deterioration, leading to global paradigm shifts in pipeline asset management. He has received several awards for innovation and industry collaboration, including the National and International Water Association Awards and the B. Hurt Award in 2016, the ARRB Impact Award in 2019, and the Monash Vice Chancellors and Deans Awards for Innovation and Enterprise in 2019 and 2013. On behalf of the Civil Engineering Sectional Committee, I wish to express our sincere appreciation to you, Professor Kodikara, for generously accepting to share your knowledge and expertise with our members of the ISL this evening. I would also like to warmly welcome all the participants who have joined us online today, and your presence and active engagement are what truly make this session meaningful. We look forward to your participation, questions, discussions, which will undoubtedly add great value to this knowledge sharing platform. Once again, a very warm welcome for all the participants. Without further ado, I now invite Professor Jayanta Kodikara to commence the session. Over to you.
Thank you very much, Kamala. for that very generous introduction. And it's also a privilege for me to be hosted by you, my batchmate, and two other batchmates are here, Saman Mal and Andradi also. So it is a very great pleasure to present this talk today to you. Let me share my presentation first. Um, okay, so yeah, I hope you can see the presentation mode.
Yes.
Thank
Yes, we
you.
can see.
Thank you. So, good evening. So, I'll be presenting on this topic frontiers in geotechnical engineering, climate resilience, and digitalization. And I'm Jayanta Kodikara in Department of Civil and Environmental Engineering, Monash University, Australia. So, I will try to cover these five topics briefly in the available time. Of course, I'll be covering these topics. Some are a bit beyond my expertise, but I'll share my thoughts on these topics because that they are relevant to current climate. So I'll first introduce this climate resilience and digitalization. Then, what are the effects we could expect on geo infrastructure, especially? Then I'll show some examples from road, railway, and slope failures, and some advances in digitalization, primarily using my experience. And then I will conclude with some proposal. So we know that climate is changing, and primarily due to greenhouse gas emissions. These two pictures are basically showing uh, the CO2 equivalent emissions with time as given in IPCC, International Climate Committee uh, uh, briefings. And you can see this red line shows if you do not do anything, business as usual, then this is the kind of increase we would get in these parts per million CO2 equivalent greenhouse gas emissions. But if we do some mitigation, such as this purple line, RCP 4.5 scenario, that means we will by 2050 or so, we will reduce the emissions and maintain. So that's so-called net zero, which Australia is advocating. By 2040-50, we will reach this net zero and then we plateau out. In any event, you are expecting climate to change uh, uh, based on these scenarios. So along with, we will also get some temperature rise. So this red line is corresponding to the business as usual. And if we mitigate, we'll get a plateauing of that temperature. So I put together these two figures. First figure on the left is precipitation, rainfall, because we don't have snow. Precipitation for Sri Lanka, taken out of the climate predictions. Uh, and this is the air temperature. So you can see going from current situation to 2100 or 2099, you can see the mean values are increasing, but you can also experience very high extremes. Of course, these points refer to various scenarios. So if we don't do anything, you will get these extreme cases. But if you do some mitigation, you might be in middle area. In any event, you are expecting precipitation to increase, but more problematic is this variation, extreme events, like the Ditwa cyclone. And then temperature is also showing similar increase with variation and extreme events. So along with that, we get various effects. We can get various effects. Of course, moisture, rainfall, flooding would be direct event. But I have put together this diagram. This is a preliminary calculation. This is the corrosion rate. If you have pipes, piles, and other things in the ground, and also in the air, this is for the ground, you can see, I have put three countries here, Australia, Sri Lanka, and Malaysia. I gave a talk to Malaysian because I was in Malaysia a few weeks back. Therefore, these three countries are shown. So Sri Lanka is shown in um, this color here. So you can see orange kind of color. So you can see it's showing the corrosion rate could rise quite significantly. So along with the corrosion rate, of course, you can expect pipelines and other things to deteriorate fast. So that's another aspect of this indirect aspect of expected climate change. But as far as the ground is concerned, what you expect is this ground above the water table. So this is the water table below which nothing much would happen. But water table can fluctuate, of course. But above the water table, you will get wetting and drying. During rainfall, you will get wet conditions. What is shown here is so-called suction, which is the negative water pressure. Water pressure is positive below the water table and zero at the water table at the water table level, and above that suction will increase, but during rainfall it will become very wet, and therefore soil will be wet and suction will reduce, and during drying suction will increase. So during wet dry this will fluctuate, and that fluctuation will cause anything buried in this zone above the water table to undergo effects of climate. Pipes, roads, houses, foundations, and so on. So that's the so-called reactive zone above the water table. Anything placed in that zone will undergo these changes. Of course, if you have a slope, then slope will have additional problem due to gravity. So I'm talking about resilience, climate resilience. So let's have some kind of definition to start with, because we may need to be clear on what resilience means in the engineering context. This is a more general definition. Resilience is the ability of a system, community, material, or individual, even individual, to withstand, absorb, adapt to, and recover from the disturbances while maintaining essential functions and ideally becoming stronger afterwards. So that's what resilience means in the dictionary. So we can consider resilience in two ways for engineering purposes. We can think of resilient materials to be used, which are having these characteristics, or and resilient processes. How do you design for resiliency? How do you construct for resiliency? How do you rehabilitate or maintain for resiliency? So those are the processes. So let's look at climate effects on geo-infrastructure, because my area is geo-infrastructure. So here I'm looking at increased precipitation, what kind of problems you might get, decreased precipitation or drying, temperature rise, and sea level, and so on. So when precipitation is very high, you can get infrastructure moisture damage. You can expect landslides, which we already know, water erosion. I will talk about that. Sometimes not very much talked about, and flood damage as well. So then, if you have temperature rise, you can get thermal expansion of pipes, so joints can buckle. Then, if you have asphalt on roads, then they can melt and rot. Excessive ground movement can happen. Increased metallic corrosion. I talked about corrosion already. That's a silent problem which is not very well understood or explored. Then, if you have drying, then you can get soil to crack or concrete to crack, and then increased settlement can happen. And of course, with drying of moisture, you can increase the salinity of soil as well. And with sea level rises, you can get inundation and associated problems. Salinity also may be an issue. So these are some of the climate change effects we can expect in geotechnical um, structures and so on. So I'll talk about some examples on roads because we have been researching on this topic for last 5 6 years in my hub. And before that, of course, I was working on pipelines, but I won't talk about pipelines today. So it will be roads and mostly landslides. So when we talk about roads, roads were there a long time ago, Roman Empire, and they had very good roads, and they maintained the empire, military, moving military, and also other goods and services through their network. Then, more recently, in 1960s onwards, um, America developed their highway system, which was actually when they developed it in President Eisenhower's time. It was a huge project, and they made it very redundant. That means it's bigger than they needed at the time. So that provided them with a lot of economic uh, activity continuously without any bottlenecks. So that was how they developed, that helped them achieving economic prosperity. Now, if you look at China, they have been doing that recently, and there is the autonomous car which I was in Wuhan recently, and I can actually run this also. But it was very interesting going in this autonomous car. So you can see how far we have come from Roman Empire to the current state. But when you come to Australia, Australia also has a very long network, like almost 1 million kilometers, because this number is old. Current number may be close to million or more. We spend a lot of money on roads, 1.5% of the GDP, and maintenance cost is also huge. Every time you see government is spending billions additional to this ongoing maintenance costs. It is the highest per capita expenditure in the world because we have a smaller population, similar to Sri Lanka, something like 25 million, but we have a huge land to cover. So, because of this reason, unbound payments with relatively thin seals have been very common in Australia, economically efficient. They cover about 90% of the seal road network. However, they are being challenged now. This concept, unbound payments with thinner seals. Seal is bitumen or asphalt, and they are using 25, even sometimes less, spray seal, sometimes 20 millimeters up to 50 millimeters in arterial roads. Of course, freeways and other things are high quality, thin, thick asphalt or concrete pavements. But for low volume roads, they have been using this concept, and that's been challenged with these climate change effects. So, what are these flexible payments with relatively thin seals? So, they have a granular base as a load bearing base, and of course, they have the seal, which can be a bitumen or asphalt seal. I told you thickness may be not as high. I think in Australia, in Sri Lanka, in main roads, they use so-called carpet, which is about 50 millimeter asphalt binder course. And I think in very low volume roads, they may be using thinner asphalt as well, like in Australia. So, subgrade is the natural ground which has been prepared for the road, is the weakest link normally. So, granular material is stronger or stiffer, and then the bitumen. So, under traffic loading, they can undergo so-called plastic deformation, which leads to a so-called rut on the wheel path, as you can see here. If you put a ruler or gauge here, a straight edge, you can see how much it has rut. Normally, we need to minimize this rut to about 20 millimeters or more less, because you can get water, planning, and it is hazardous. Driving quality goes down, and also cracking can happen, which allows more water to get in, and then potholes and other things quite common. Normally, this problem is more in the outer wheel path if you have multiple lanes in one direction. So, this rutting is the primary distress mechanism for these unbound payments. And of course, stiffness is also very important in this load bearing unbound layer, because under wheel load, if the stiffness is low, load will directly come into the weak layer subgrade, and you can get more rutting, because rutting can happen in subgrade as well as the unbound layer. But if the modulus is high, stiffness is high, then it will be spread, load will be spread over a lower, much wider area, and therefore subgrade will get a smaller stress, and therefore it will not rut as much, but still rutting can come from the unbound layer. So the stiffness has this kind of shape with water. So here water is represented by not moisture content. I am representing it by degree of saturation, because degree of saturation means, in unbound material is crushed rock or something similar. It could be recycled material, it could be recycled concrete, it could be gravel taken from a nearby quarry or crushed rock. So either way, you have these spaces between aggregate, so that holes are voids. So you have void ratio or density. So if the voids are completely filled with water, your degree of saturation is 1. If voids are completely empty, your degree of saturation is 0. So in between, you get the amount of moisture giving degree of saturation going from up to 1, right? So in that context, you can see if degree of saturation is increasing, then initially modulus goes up to a certain peak and then drops down rapidly as degree of saturation approaches 1 because of the effect of moisture. This line here shows the rutting or plastic strain, rutting. So rutting continually increase with the degree of saturation and rapidly increase as it approaches degree of saturation 1. However, performance losses can occur even before saturation. See, around here, 95%, 90% saturation, you still get significant rotting. But if you go to saturation, of course, you get excessive problems, something like flooding. Under flooding conditions, if the moisture get into the pavement, you can experience a lot of rotting. But moisture may not get in if you have a good seal, right? Your seal performance is paramount. So I'll talk about that later also. So if degree of saturation increases, stiffness can drop, permanent strain or rotting can go up, and potholes is also can happen with cracking and so on. So these are some of the pictures from local conditions in Australia, especially related to Queensland. Recently also they had flooding. So rainfall in Queensland is in 3,000 millimeters or 2,000, 3,000. If you go further up to Cairns and so on, you can get even higher in the coastal area. So flooding is common, right? So you need to deal with this flooding in roads especially. So this picture is also from Queensland, and you can see traffic lights, right? So that means it's like a lake. Roads have all totally submerged. So these are the kind of problems it will arise. Then potholes can arise on here. Of course, this is a low volume road, not a freeway or you know important road, but this is also important for that community. So you can get these kind of problems and flood damage. And if you have, so Australia also has significant number of unsealed roads. Unsealed means no seal. So it is unbound payment only. So they can develop all sorts of problems. Corrugations can develop, water erosion can develop, and so on. Then, of course, excessive rotting. So we have actually, instrumented the payment in Queensland, and we measured the moisture variation in the payment with time over a couple of years. So here, a 50 millimeter asphalt layer, which is a good asphalt thickness, not a space seal or anything. So, which I like, about 50 millimeter. So similar to, I think maybe also, your good quality roads in Sri Lanka, and then you have a layer here, base, and this is a sub base, and then the subgrade, right? So normally base can be divided into two parts: good quality crushed rock as base, then marginal material or lower quality as sub base. So we monitored this in this road here, and so these are the three graphs you can see. This degree of saturation. Degree of saturation variation with time. So 0 to 700, so roughly 2 years. So you can see top one is subgrade. So from the starting point of the pavement construction, there was a new road, and then it has saturated and it stayed pretty much around about zero point 0.8 saturation throughout, right? That's common for the subgrade. And then the base is the uh, blue line. So you can see it has initially start from dry conditions because there's a practice in Queensland to dry back before you put the seal. So it is degree of saturation is low, and then it has gone up, and then drying, wetting, and it has undergo these cycles along with the rainfall, right? So you can see even with this thicker seal, still moisture has got in and it has responded. And this green line is for the sub-base. Sub-base has also behaved in similar manner. So you can see moisture has rainfall and climate has influence on the moisture which comes to the pavement. So this is a model that has been run for these conditions using finite element modeling, simulating the climate, and it can qualitatively capture this, not exactly the model, but very close to what has been observed. So modeling capability is there. to see the climate effects. So this is temperature. So temperature affects asphalt. Moisture affects soil and aggregate under base and sub-base and subgrade. They are not affected very much by temperature, but temperature, air temperature, affects the asphalt, and it can undergo rotting and shoving and cracking and all sorts of problems. So this diagram is actually very crowded, but let me simplify it to very simple way. So this is from Nature, actually, Nature Climate Change. So it's a very good journal, and it's written by somebody I know called Underwood, Shane Underwood in North Carolina University. And he has used USA conditions. USA has a lot of asphalt pavements. This is the high scenario. That means CO2 emissions continue to grow without any mitigation, right? You saw that red line I showed you earlier. So if you use that scenario, you will expect this kind of change in temperature. This is the low scenario with mitigation like net zero. Then the cost in impact because of this temperature rise. 2010 to 2070, you can see in the mitigated scenario, it is still reasonable cost increase. And this is the high scenario, significant billions of dollars, almost 4 times now to 2070, right? So this is assuming we don't change any practice, design practice, material quality asphalt. If we don't change from current situation and build our roads and maintain them, this kind of damage could occur. So he was proposing we need to change our practice and use higher quality asphalt and things like that. Do not use the current specifications. In fact, I was in Malaysia about 2 weeks ago, and they are actually changed the asphalt quality already to respond to these damages, right? Which is interesting. So some advancement on road payments. So based on our research in recent times, what we have advocated is to capitalize on this, digitalization, advances in AI and data collection, and so on, and add resilience, climate resilience to the payments. In order to do both, we have to integrate these processes in any design in civil engineering. What does that mean? So, as far as roads are concerned, we have to test materials and get information, density we need, and the moisture content. We are talking about unbound bases or sub bases. So degree of saturation also comes in from that, and the modulus. So those are the key things we measure. And of course, rutting is the one which we are trying to limit, and we do the design based on these testing parameters, and we construct based on those parameters and design directly with according to design. So performance based construction. Currently, we don't do that. And then assessment, condition assessment, we still determine these parameters, how they have evolved, and then feedback loop. So that will provide us so-called feedback and data driven asset management. So that's what we proposed. Currently, these processes are disparate. That means they are not connected. Therefore, this integration is not possible. If you don't integrate processes, then you cannot get the best benefit of digitalization. Processes must be integrated. Information should flow from one to the other, and then you can utilize the uh, collected data to tell you what might be going wrong what can be done to improve it, and so on, right? So, a so-called digital twin is a concept that's proposed to house that process. So that's what we have been advocating. But if we go back to our current specification of these unbound layers, currently we are very simply doing this. We are telling in the compaction plane density against moisture content, so-called compaction curve, Proctor's compaction curve, and there are multiple curves we can get for different energy levels. These called modified Proctor, higher energy. These the normal Proctor, and then even higher. So they may represent bigger rollers, if you like, smaller rollers, handheld, bigger rollers, and even bigger 20-ton roller, and things like that. So what the current specification does is it get this maximum point somewhere, moisture content is specified, maximum density is specified within some tolerance, and then construct payment to these specifications. So rollers will have to go and densify to get this density, and the material is prepared at this moisture content. So this is traditional approach, but the problem with this is you can end up in this red line is the line of optimums. You can end up on the wet side of this line of optimums. Then as you saw that SR curve, remember the rutting curve went up very rapidly when you approach saturation. This is the saturation line. You can get a lot of premature failures. So that has been already observed, and because of that, pioneered by Queensland Main Roads, they have asked, okay, you can construct here, but you have to dry back before you put the seal. You have to reduce the moisture up to here, and then only you can put the seal. Don't put it here, because even you can go, you cannot really go to this one. Sometimes you go up and so on, then problematic. So that's the current practice. So in order to test materials, we develop a new testing method. We call it CRST test. That's a fairly mouthful, constant radial stiffness triaxial, but don't worry about that mouthful. It is CRST, right? It's a very simple device. It's a compaction mold split into pieces. When see these pieces, so they you get bunch of pieces. Then you put into this cylindrical mold, but in order to keep the thing, you put a band around it. This band, that's called a stiffness band. So when you compact the soil, we have the stiffness, and we compact the soil in traditional way using a hammer, and then we conduct the test by cyclically loading to simulate traffic loading. Then you can measure the amount of rutting that might develop in the pavement and also the modulus. You can measure both rutting and modulus with this test. So this test is much simpler, and it is very rational. It take into account the pavement behavior more closely, and it is easy to do and to cheap to procure. So normally when we do a smarter, we call it smarter test as well. If you want a smarter, more rational, advanced test, it will be always very expensive and complicated. In this case, opposite. It is simpler, it is cheaper, but you get better results. So we were proud of that achievement, and currently Austroads is investigating, adapting this to Australian practice through NTRO. NTRO is doing a research project at present. So that testing allowed us to produce this kind of graph. This is first time this kind of graph has been developed. So we have the density, again moisture content. So these graphs are contours of rutting. So 1% line is actually 1% rutting. 1%, okay, let's say 5%. 5% line is this line, right? That's the 5% line. So 5% rutting means if you have 400 millimeter unbound layer, 5% rutting means when you undertake a lot of cyclic loading traffic, you get 20 millimeters at the end. So that's the limit we like to keep. So if you, in this example, if you go to this point and compact your unbound layer, you will expect about 20 millimeter rutting at the end after design life. But you can see if you go to this wet side, these contours get congested and you get more and more rutting rapidly. But if you dry back, like Queensland Main Roads is advocating, if you dry back to this smaller moisture content, 6% instead of 8%, you are getting 2% rutting contour. You are on the 2% rutting contour. That means your overall rutting at the end of design life is still 8 millimeter, much better. So you get better performance by drying back. So this is the first time it was demonstrated by this test. Actually, this simpler test allowed us to do many tests and get these contours. Nobody has seen these contours before, right? So that is advantage. So next one is we developed a design method to go with the test. So to compute rutting with time, with traffic loading. So this is an example. So this is the model, but I wouldn't dwell on it. So input is density, degree of saturation, and the stress that is coming from the traffic load. And here you can see the 25 millimeter asphalt layer here. That's what we call thin seal. Then the granular layer here and subgrade. So this is simple road which has been simulated. So here rut development with time. These are the load number of load cycles. So you can see this green graph is actually how rut will develop, but we will not take the climate effects into account. That means any moisture coming in through this pavement. We haven't taken that into account. Then you will get this 10 millimeter rutting at the end. But if we allowed the climate to interact with the pavement, you have this curve, which is now rutting at the end of these load cycles, has gone from 10 millimeter to about 25. So it has significant rut development when the climate effects are included. However, this is for the seal of 10 to the minus 7 meters per second permeability. That means relatively permeable seal that allowed more moisture to come into the pavement and drying to happen during other times. Therefore, you got this effect. So if you have a seal which has low permeability, 2 orders of magnitude, good quality seal, then the effect of climate is much reduced. You can see the two curves are very close to each other. That means climate effect is reduced. So what does that highlight? That highlights the importance of the seal and maintenance of the seal. So seal can be high quality seal, better binder, or you can increase the thickness, right? So we are advocating that this law in Australia to not use these very thin seals, especially spray seals. Use asphalt seals, and I would prefer it to be 50 millimeters at least. And then what happens then is moisture effect is reduced. When moisture effect is reduced, unbound and subgrade layers are going to perform better as you expect. When they perform better, no rutting. Because of no rutting, seal doesn't bend and crack. Because seal doesn't crack, moisture won't get in, and both work in synergy and you get a resilient pavement. Otherwise, you get a deteriorating pavement because when unbound layer moisture gets in an unbound layer rut, cracking the asphalt layer will bend and crack, more moisture will get in, and deterioration will get continually. And potholes and other things are the result. So this is a very crowded slide again, so I wouldn't dwell on it too much. So basically what we are telling is what are the features we like to have for a resilient materials. So this may apply not only for payments, any other material we use for construction, buildings or whatever. So we can expect loading spikes under climate effects, and they should be strong, but they at the same time they need to be ductile rather than brittle. Normally when we make something strong, they become very brittle, cracks. Concrete very strong, we add cement and make it strong, but they become very brittle, they crack and break very quickly. Needs to be resilient against cyclic loading and wet dry cycles. Needs to be resilient against erosion under fast moving water or air. Needs to be resilient against elevated temperature and cycles of temperature. Needs to have low carbon footprint and recyclability, that is for the mitigation of climate effects. Needs to be resistant against possible combinations of the above stresses. All of these may not be needed for a certain application. Some applications, one of these aspects may be the most dominant criteria, but these are in general terms. And if it is self-healing, that will be even better, because human body and animal body or those things have the self-healing capability, right? So if there's a damage, cut, it self-heals, right? But materials don't have that kind of capability unless we build into it. Of course, many research is going on similar things. So here, some examples of resilient material. Again, it's pretty much done in Queensland more, because that region is prone to this flooding and heavy climate effects, cyclones as well. So this material is called formed bitumen. Formed bitumen is aggregate, like crushed aggregate, and you add bitumen and also cement or lime to add some strength. So cement or lime adds strength, bitumen adds flexibility and cohesion. So how does it happen? So you send the hot bitumen here, and then you also send water and air here. So when those three things mix, you get foam, high temperature foam bitumen, and you put aggregate here, and they all get mixed up, right? And also put the cement, they get all mixed up, and you get this foam bitumen, and that is used to build these roads, and apparently they have uh, been very resilient. Even after flooding has gone away, road has withstood without failures. So there are examples like that we have heard from practitioners in Queensland main roads. So that's one possible resilient material, and we have investigated how it does it, and it is something like this. So strength and strain. When we get concrete like materials, lot of cement only, we get high strength, but it's very ductile. Sorry, it's brittle. It comes down, strength comes down. Once it fails, strength comes down rapidly and break into pieces or cracks. But if you see metal like steel, they are strong as well as ductile. You can see this ductility. With strain, it maintains strength, it doesn't come down. So this material also has something bit closer to that, but not like metal, of course, because it's not easy to make it like metal with this combination, but it has this effect. Therefore, it can resist moisture effect as well as cyclic loading effects better. But if you go to nature, you know, your humble spider is actually doing it already. if you get these from a Nature journal, some publication given about how spiders' webs perform under different loads. So what they do is they create two levels of webs. One is this spiral web, which is like this blue one, and they have red threads, which are much stronger. So they do two different functions. When you have a main function of the web is to catch flies and other animals, insects, small insects, and they need to be sort of taken back and stopped, and then spider can go and eat. So it shouldn't be too rigid, then it will fall off. So it needs to give way and catch it. So it has that kind of stress strain relationship. But if a heavy wind comes or some debris comes and hit the web, it has to be strong. So then this red spiral will activate, and it has very high strength, and it only activates when it has deformed reasonable amount. You can see this one, right? So that is a concept nature has used. So similarly, we could use this an example in geotechnical engineering. If you have a shallow foundation, footing along with the pile together, you can get this kind of behavior. In small loading, shallow foundation will respond, but deformation goes more, deep foundation will come into play and resist the loading. So similar concepts now currently being proposed in wind turbines, if you like, under cyclic loading and so on, in seabed and things like that, where heavy loads can come and structures can be very large, up to 100 meters or high wind turbines. So now I move on to landslides. So this topic is, of course, something I was in Sri Lanka in the December after the Ditwa cyclone, and also in January. So I had time to study some of these there while I was affiliated with NBRO, National Building Research organization or institute, working also closely with Professor Atula Kulatilaka. I think Atula is here somewhere. I saw his name. So he was the person who is pioneer in this area. I am, of course, still learning. So I will share my experience with you. So Ditwa, Cyclone Ditwa happened in during 27, 28 November 25. So I went to Sri Lanka on the 4th of December. Things have happened then. So it had heavy rainfall, 400 millimeters in one day, and severe winds, landslides, so more than 1,200 landslides, mostly in Kandy, Nuwara and Badulla regions, and flooding inundated 1.1 million hectares, 20% of the land area, and so many fatalities, and 400,000 people affected. Still, some of the people are being repositioned. So massive infrastructure, housing, agriculture, business damage, about $4 billion US dollars. So it's a large event, 1 in 100 or more event, and probably attributed to changing climate. So this picture, I was given this diagram by Dr. Asiri, director of NBRO, when I visited them in December, and they produced this diagram soon after the Ditwa cyclone. So what you see is various landslides marked with dots. Bigger the dot is bigger the landslide and damage, and there are more than 1,177 at that time, soon after the cyclone, and different regions, number of landslides for each region, and how many buildings were affected is also categorized. It's amazing how this was done so quickly. It was done by satellite imaging. Sentinel-1 satellite, which uses radar, Sentinel-2, which uses optical. So this one is based on optical, I think. They use this satellite imagery to come up with this figure. So they are very advanced on that area, and they have done a fantastic job responding to Ritva cyclone aftermath. And so I was privileged to learn from them. And Dr. Professor Kulatilaka was also pioneer in that with that organization. So here you can see I have broadly, based on my observations, I broadly classified these landslides into three categories. One is called debris flow. That means you can see the picture here. It can initiate the landslide on the somewhere and goes like a mudslide and get more water and material and travel at massive speed, and eventually a mudslide, and anything in the way is destroyed as it goes. So that can go kilometers, and I have heard it has gone even 5 kilometers. So you cannot really protect very easily against such a debris flow. Very devastating. Second one is slow translational or rotational compound, but deep seated. This debris flow is more shallow, right? And might go in a certain channel as well, like, water. It likes water, so it follows a certain creek or channel. Whereas deep seated landslides might cover a large area, and it has a telltale signs of scarp development or crack development, and start the cracking here, and you can see the exposure of the soil underneath, and slowly it moves. And it may not translate to a mudslide, but it may move with rainfall. Sometimes it will move a little bit, and then more rain, it can go more. And these are problematic also, because if you have people living in this area and it's also covering a large area, how to evacuate them and put them back? When do you do that? Because it has not moving anymore, but it can move anytime, and it can become a bigger slide, but may not translate to a mudslide like this, but still can do damage. So there are other categories, lots of smaller, medium to small landslides, several meters, 10, 20, 30-meter kind of landslides, and mostly cover in the roads and other places. So they are a problem and headache mostly, right? If somebody is there at the wrong place at the wrong time, can get damaged, but otherwise it's mostly a headache. You have to remove the raw material and get passage for the traffic. So this is one of the landslides which has happened during Ritva, and you can see it is more like large area, and I'm not 100% sure whether this was a mudslide or not, but it has translated to a large landslides. So extreme rainfall, infiltration, and seepage buildup in the residual weathered slope, and major compound failure initiation near the crest, downslope mass movement and widening, deposition and burial of the lower settled area. So that's the kind of interpretations. You can see some houses damaged and so on. And rock may be exposed. So the soil which has traveled this above the rock at variable depths. So which is very common in Sri Lanka with the residual weathered profile. So here I am giving some of the interpretations. Of course, drainage may be the main thing, because you may need to control at the top, but it's not easy in an area like this. Even if you build retaining walls at this level, they are not going to be effective because these are large landslide. It will destroy the retaining wall on the way. So this is another slide which has happened, and you can see there's a minor slide here, and this is the other slide, bigger slide. So that means this slope is, vulnerable, and it's too steep. Although it has a lot of vegetation, still it got drenched with rain, and even with vegetation, it didn't help, because vegetation can produce some binding effect with the roots, but it is up to a certain depth only. So if failure happens below that, then vegetation is a problem because it adds weight and it goes down with it, right? So vegetation is helpful, but not for a deeper landslide. Another thing is how to now prevent this happening. It is basically difficult. So drains and maintaining and berms and so on. But of course, with a large area like this, it's not easy. So mechanism is extreme rainfall, suction loss, seepage concentration, shallow translation failure in weathered mantle, debris movement downslope, road interruption, and so on. And it has almost gone to this level. So this is another example where landslide started here. This is the aerial view, and it is more like a slide. It has gone down like a slide, and then covered the railway line and also the road down, right? So so of course, shape suggests a failure dominated by a shallow translational sliding and debris movement, not a classic deep rotational slump, right? Traditional thing we see in our soil mechanics books, a circular failure, they are not seen here. None of the circular failures was seen in these landslides. So again, infiltration need to be reduced somehow, and the drainage need to be reduced. The drainage needs to be facilitated in the toe areas and so on. So I go back to the this one here. This is interesting one also. So you can see this is next to the railway line. So this is actually rainfall induced shallow compound slide. So you can see these erosion gullies. Lots of erosion has happened. So that means a lot of water has come to this side, and presumably from this side, water which came from the other side and then came under the ballast, because ballast is very permeable, and then emanated from this side and created water pressure to this side. And because of crest area is like having a lot of water pressure, that created the slide to happen, and then erosion also accelerated that. So that's intercepted drains. If you create intercepted drains here on the slope side and maintain them, may have helped this issue. So that is one thing one could see. So of course, drainage is a paramount thing preventing landslide. So this is an example I have taken from thesis that was done very recently, 2025, and it was supervised by Professor Kulatilaka, and Milinda Amarasinghe is the author. And in this picture, you can see these are the drains you were talking about at the crest level, top level. So removing water coming into this slope. And of course, having this surface vegetation helps you, erosion, primarily erosion. However, it may allow water to infiltrate, right? So vegetation has help. Roots can provide some binding effect to a certain depth, but not deeper. but it can reduce erosion primarily. But when the water is moving slowly, that can provide more infiltration. So it can have beneficial effects and also non-beneficial effects. If it is a big tree, then it can also add weight, even under cyclones. So you can have these kind of drains catching the underground water, and in three-dimensional sense, it will be a network, and then eventually drones and drains at the front as well. So drainage is a primary mode of protection at various level. Surface drain, the starting with, then the subsurface drains, and of course vegetation or other protection, geosynthetic and other things. So some of the slopes that have been rehabilitated in that fashion, also soil nailing is done in some instances, soil nailing into the wall. But this is one example which has, didn't undergo any failure, which has good drainage provided all around. As you can see, these cascade drains, these are retaining wall, and these are drains all around, and vegetation, and so on. So this is actually Atula, and this is, I think, Bandar, I think, Kane Bandar from NBRO, Professor Atula Kulatilaka. So they are the guys who um, pioneered this kind of stuff. So it has toe support, surface geometry improvement, good surface and subsurface drainage, and weep holes. Very important. You can see if you don't provide weep holes, then water has no chance to get out and drain from these retaining walls. So if you close them, you're asking for trouble. So, and if you have this drainage, maintenance is a paramount. So, how to maintain and clean these drains? They can get clogged, and then drains and drains. They don't work. So problems can arise. So we also found so-called erosion problems, right? Erosion is sometimes forgotten, and in Peradeniya University and Peradeniya gardens, I went around them. Huge amount of erosion, right? River went very high and eroded surrounding areas. So this is an erosion problem, not a slope failure as much. This is, the railroad. So it eroded when the moisture came from the other side. It eroded the ballast and the surrounding area, right? Realistic scenario may be heavy rainfall infiltrated the ballast and shoulders from the side slope. Interceptor drainage was not provided, and water concentrate to a downslope. Fine material was softened, washed out, outer shoulder progressively slumped, ballast and subballast lost confinement, and so on. So these are more erosion problems. These are another erosion problem, and it can translate to some kind of a slope failure as well, but primarily it is erosion. These sandy soils and so on, which residual soils in these regions, silty sand, sandy silt, that kind of soil, loam kind of soil, they are pretty much erosion susceptible. So I also looked at this Morgahakanda bridge failure. So this bridge in Morgahakanda failed, and that is the eventual sort of picture of failure. So this part has gone. But actually, when you look at it closely, it is not the bridge that has failed. Bridge here is this part. It hasn't failed at all. Only thing is huge amount of the supporting approach abutment area has been eroded. So if you go here, you can see this is the Morgahakanda Dam, and that has been overflowing. So all the sluice gates were open, huge amount of water was released. Normally, water goes in this path. So water goes like this and turn around and then go under the bridge. So that's the bridge, right? So, but when huge amount of water came, what it did was water went straight through without bending and eroded this whole area apparently. And you can see this area apparently has eroded. So that's the area which is seen here, but the bridge part is still there. So erosion happened because water decided to go straight through. So this is, I saw these pictures from YouTube and other places. So this is the bridge part. It hasn't failed, it's still there. So the approach which has eroded, now this approach has been rehabilitated. So they filled it up and put the road back on, right? So that's where the erosion happened, this part. So bridge is okay. So you can see problem is associated with something else, erosion. So now I think you might find if this was not constructed properly, this will settle with rain and undergo multiple failures. So of course they need to address this. It's good to get this done quickly, but it may suffer unless it's protected properly. So erodibility of soils is important then, right? Landslides is one aspect, but erodibility of soils is very important. Silty loams and sandy, silty sand and sandy silts and so on, highly erodible. This is so-called erodible factor. But erodibility is not only erodible factor of soil, it also has, rainfall, how much rainfall you get, what's the intensity and the slope, you have vegetation, you have any supporting structure like drains. So they all determine the soil loss. So one has to pay attention to those things. So I also had a look at this so-called Yakapalama in Peradeniya University, or Devil's Bridge, or Kalupalama. Water has gone over it, and it has undergone severe distress and it has bent, right? So I took this picture because I actually walked on this bridge that day when I was there. And at that time, there's army or sorry, navy. Navy was cleaning this area. And you can see this middle pillar has tilted, middle pillar. Other two pillars are okay. Middle pillar has tilted. Along with that, the whole railroad has bent, right? Significantly bent. And but when you look at it, what has actually happened is huge amount of this debris, mainly, this bamboo has come with the erosion. Sometimes the whole bunch of bamboo has come and trapped in front of this pillar, and that created the large force from the water on the pillar. So then pillar from the ground shifted and erosion happened underneath and therefore it shifted. Luckily it didn't collapse. Now they are rectifying that, right? So you can see people are removing this, but eventually they had to get special equipment to remove that. Because in 1940 something, there was a similar flood in Peradeniya, and that time also water went above the bridge, but different bridge, smaller bridge. That bridge went away, but the three pillars were standing without any problem. So water alone cannot actually damage these pillars. Water can go around it. But unless you get this huge amount of debris that will come and trap and create this force over a wider area, and that force can become massive. So that's a resilient issue to contend with, this debris flow in rivers that can plug things, drainage outlets, and so on. So that's an important issue. So some digital advancements. So when we construct, I said intelligent kind of compaction. So this is a device we have built ourselves. This is, of course, two other devices were built, but I'm only talking about this because this is ready to be deployed in practice. And so it's a plug and play device. So it can give you with rollers the coverage, how much area is covered and how many passes it has done, some level of quality of compaction. So three things it can give. So we are now trialing this, and it's ready to be deployed. So if anybody wants to trial this, please contact me. So we did a lot of experiments to develop that under various conditions. And this is an example. We tried it in Victoria, in Melbourne. This is the coverage map, and this is the quality density ratio that's achieved with PAS. And this one shows 25% of the area got 94% of the density we need, 31% got this, and so on, and higher density small areas. So if your target is this, then you know some 25% didn't get the density you want. So you know entire corridor, you get this information. In contrast to current practice, where people will measure at some spots using nuclear density gauge, whether density has been achieved on that spot, 10 spots for 100 meters of road section. But that may mean many areas may be missed. But here you get the full coverage, and you can go and rectify it immediately. And for the engineer in the office, will get this mobile phone outlet or in his computer what's going on. So this is something we developed ourselves from scratch with the electronics engineer, and we are now almost ready to produce it. So remote imagery, remote sensing is very important in digitalization. So I told you satellites, aircrafts, and drones. Drones missing. So they can actually get a lot of information. So in geotechnical engineering, I think people are not using as much, although in NBRO, there is a division on spatial technologies, surveying, spatial, and they have experts in using these satellite and drones and so on. And you can get information on the ground deformation, even up to cracking in buildings and deformation due to subsidence. Those things they have covered, and I think that's an area which can be very useful for, and it's an emerging area in our field, although it has been used in other areas before. So, in concluding remarks, I am sort of proposing some change in practice, introducing a new concept of resilient modeling or resilient assessment. So you can design your things under current loading conditions, current specifications, current design guides. However, do a test for expected extreme event, such as DITWA, right? And see what happens. Of course, we cannot design it for 1 in 100 year event. We can only design for 1 in 10 or whatever event. Otherwise, our structure will be very expensive. We cannot afford that. But you can do a test with an extreme event. How much damage will happen? Oh, like Morgakanda Dam, if all the suitcases are opened, water can erode this area. So we need to provide riprap and strengthen that face of the river, so that water can not erode, or use some material non-erodible, right? Less erodible. So those are the some additional supplementary work you can do after resilient modeling. We see some vulnerabilities, and if we spend a bit more money to rectify them or retrofit them, then you can have a resilient, because some damage will happen, but it can be reused quickly. It won't destroy the whole thing. So that is something I'm proposing based on this practice, some additional concept to be considered in civil engineering practice. So with that, I am concluding my presentation. Thank you very much. So if you have any questions, please feel free to ask.
Yeah, Kodikar, I just wanted to, comment something
Yeah,
for the landslides, because I am looking after the landslide in the TMR
right.
in metro region. And I think recently what we have done, I think we did some sort of, the monitoring system.
Yeah,
It's one of the we used um, the survey instrument with 45 sensors
yeah.
we install in the at the whatever the slope, and it will give us the what is the movement of. It's every 2 weeks. It is connected to our computer, and it will come to our computer every 2 weeks. Then I think surveys they process it and send it to us. We just the check how much of the movement for uh, each fortnight. And for the Sri Lanka, can't we do some sort of this type of the monitoring system where we have a vulnerable the slopes?
Yes, I think very good suggestion. I think they also have so-called early warning systems. NBRO is responsible for issuing early warning systems. You
Yes,
might have seen certain areas given that warning after certain rainfall events because most of the damage is rainfall induced.
yes,
So of course, problem with Sri Lankan context is it is so many of them are there. So you can see 1,500 landslides, and I
okay,
showed you areas you don't know where it would happen, right?
yes,
So
yes.
that complexity, it's a blessing and a disguise that terrain. It is interesting, very nice terrain, beautiful to look and so on, but so many steep slopes and so on. So of course they are having these warning systems. They
Yes,
include some inclinometers and things like that, as you
yes,
suggested.
we use that, yes.
But limited, yeah, limited, unfortunately. Of course, they cost to maintain and so on.
Yes,
But
it
there's
will
in
cost.
drones and satellite is a much broader sense device. You can get information. So that's what they have resorted to that more, I think.
Mm-hmm. Normally, I think, then in NBRO, do they have some sort of, the regular inspection system set up?
I think Professor Atula is here, so I wonder whether you could answer that question.
Yes, in identified critical slopes, we have different kinds of instruments like extensometers, inclinometers, strain
Yep.
gauges, and things like that were installed in identified critical slopes. Actually, it is sort of not practically possible to have them at each and every slope, but identified critical slopes,
Yep.
those instruments are installed. Now, even after rectifying slopes. So in rectified slopes also these were installed for us to see whether the rectification is properly working. So we can't have it
Okay.
practically at every slope, but certain number of slopes were instrumented.
All right. Okay.
But the sheer scale of things is overwhelming. That's the problem.
Yeah, so we monitor the rainfall. I mean, at more than 350 locations, there are automatic rain gauges, which gives the rainfall record. So that is easy,
Yeah.
but specific instrumentation is only at limited identified critical slopes.
Okay. How do you define the vulnerability of the slope? There should be a criteria. In here, we have the criteria, and we go to the site and check everything. And then I think one of the, the geologists, they go and, they inspect, and they follow the criteria, and they give us the ARL number. That is, ARL means uh, assessed risk level, we call that. Then I think ARL 1 is the worst, ARL 5 is the we don't want to do anything. Therefore, do you have that type of the system set up?
Mm, e- Yes, not a standard system as such, but so there are regional officers of NBRO all over the country in the critical regions. So whenever we get some information, or I mean, geologists visit those areas and observe the features of instability, and if there are sort of critical situations, then monitoring is done through installation of instruments.
Mhm.
Yeah, I think the early warning system actually has various
Yeah.
inputs.
Early warning system is sort of primarily coming through the rainfall measurements, but in identified critical areas, so we have these different types of instruments installed, but in addition to that, I mean, every sort of reported suspected slopes are visited by the NBRO geologists and engineers, and
Yes.
they are keeping an eye on that.
Okay, right. Okay, thank you.
I think, can I ask one question from Professor Atula?
Yeah,
Yes,
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 yeah.
go ahead.
I think by now NBRO have their own procedure of identifying the most critical areas and moderate and the minor, according to my understanding, because I have been involved with this disaster management project. So,
Yeah, yeah,
according
because
to, I
that,
think, their plans, they are preparing a lot of designs and some structure designs
uh,
for their preventive and the preventive, actually mainly preventive. But according to my
no,
understanding, what is lack
yeah,
is for the
no, because
severe slopes, severe embankment, and severe, I mean, the forest areas like that is the main understanding. I
uh,
think we are in a lack of.
no. No, now there is this landslide hazard zonation project, which started in about 1995. So critical about 13 districts in the central part. All the areas, the hazard level has been mapped. Initially to a map of 1 into 50,000, then subsequently to 1 into 10,000. So there's hazard zonation maps. So which gives areas there are no likelihood of landslides, then the three more levels of susceptibility, that is low risk, medium risk, high risk, like that. So those that had been done. Then specific areas related to by the sides of infrastructure, roads, schools, hospitals, and things like that. So there are reports coming from regional officers, so even sort of RDA and other people living in these areas. So over the last, say, 10-15 years, we have rectified about 300 to 250, 300 landslides. That is susceptible areas. There was a project started in 2012 under the World Bank funding on Candy schools and number of sort of Candy Mayangana Road and sort of number of places like that.
Mm,
So
mm,
there were cases where landslides have occurred. Then there are other locations where landslide could occur. So
mm,
so those locations were rectified by engineering means, that is primarily attending to drainage, surface drainage, subsurface drainage, When that is not enough, reinforcing with soil nailing, construction of toe retaining structures like that.
mm,
I mean, very
mm,
site-specific rectification measures were designed by NBRO and
mm,
implemented at about, say, about 300 locations all over the country. And we are happy to say that none of those rectified slopes uh, were damaged by the Ditwa landslide. All those rectified slopes were standing very well,
mm, mm,
withstanding very well the impact of the Ditwa landslide, the Ditwa cyclone.
mm.
So
Okay. Thank
currently
you.
now the after the landslide, so NBRO is given the sort of the responsibility of looking after rectification. So now
Mm,
we have teamed up with engineers from RDA also, and we are doing the landslide rectification, the corrective rectification designs for those
mm.
that happened during the Lita cyclone. So because of the large number, so it will take some time. But NBRO is working full time on that.
Thank you.
And other thing is, I think, Atula,
Yeah.
yeah, I think I watched a lot of, the videos during this, the Ditwa cyclone. I think some of the slides, because of the lack of maintenance.
Uh, yes, I would say so. That actually we visited many sites. On
Yeah.
large number of sites, the prime reason was poor drainage. So I saw a number of places where the roadside drainage, the side drain is had been discontinued. Right? So then the water
Mhm.
overflows, goes down to the slope, and slope fails. On many, I saw at many locations, the primary reason was poor drainage because
Yeah, yeah, yeah.
the drainage facilities had not been properly maintained or not properly constructed. Yes.
There is a question in the chat section. It's asking what are the possible design or stabilization techniques to prevent road asphalt pavement crack due to expansive soil behavior. Um, of course, expansive soil behavior is in the subgrade. So subgrade, in order to expansive soils to deform, you need moisture change. If it is totally wet, it will be swelling and then it will be very soft. Then, of course, you get a lot of distress by rutting and so on. But if it undergoes wetting and drying, then you get expansion and contraction, drying and wetting. With drying and wetting, you can get the pavement responding to that and develop cracking and undulations. So, in order to prevent that, best approach is to stabilize the subgrade.
Mhm.
So you have a certain layer of subgrade up to about 200 mil or whatever. You cement stabilized or lime stabilized and reducing its expansiveness, and then have the pavement. But if the pavement is already built, then only option is to reduce moisture change by having a good seal and side drainage and not allowing water to get in and out. So cutting off moisture change. But I'm not sure how much of a problem expansive soils in Sri Lanka. Atula can probably help, but
Mm,
most of the soils we have seen mostly these residual soils, right? That's a problem actually for slopes. These sandy, silty, moisture can get in very quickly and they cannot hold much suction. And whatever the suction they have can diminish quickly because moisture can penetrate easily and eventually slides can happen. So, Atula, I don't know
yeah.
whether.
We have encountered expansive soils in Dambulla area because I did a research project with one of my students that is Dambulla Kurunagala boundary. So the highly expansive that has a swell pressure of about 180 kilopascals. So Dambulla, Anuradhapura certain areas, Hambantota certain areas, we have identified the presence of expansive soils. So sort of in local areas like I mean it doesn't mean all of Hambantota or all of Dambulla. In Dambulla, Kurunagala, certain areas, certain regions, expansive soils also identified. And so through Enviro actually we have sort of uh, given them advice as how to improve the situation, how to do the rectification and construct the buildings with that.
What type of treatment do you do for the expansive soil in Sri Lanka?
Mm, Actually, in those cases, what we have done is we have identified the depth of the expansive material. So, and replace that under the foundation influence area with non-expansive material, and
Yeah,
then
yeah,
improve the drainage. That
yeah.
is, prevent water getting into the area. Now, if it is a building, put the drains and let the water flow away from the building, right? So you can slope the ground around the house to sort of make sure that water flows away, right? Sort of prevent water getting into that area is one thing. Other thing, under the foundation, replace that expansive material with
Yeah,
an
replace
unexpansive
it.
soil.
Yeah. Okay.
Any more questions?
Hello, can you hear me?
Hi, hi, Samanmal.
Yeah, I'm Saman Mal. I'm Professor Kodikar will be aware. I'm from Queensland. First of all, I will thank you. I mean, explaining the things very, very slowly, clearly, which took me back 10, 15 years what we did in Sri Lanka. So thanks for that. Um, question, what I've thought of explain to you now. You mentioned on that resilience material concept, you
Mm.
mix bitumen, water, and air.
Yeah.
Normally, I mean, we understand that it's a bit hard to mix water with bitumen. So, what sort of a technology you're using for that? And my second question is, that's you have shown that Yaka polymer. I also noted in that most of what has happened there, that center pier, it's tilted towards the water flow direction. But normally, I mean, our feeling is it normally that whatever that things in the water, it will go with the water flow direction. And what made that issue there, Professor Kodikara?
Yes, the first question is um, um, on the sorry, I forgot the question. First one
No,
was
making the material, I mean, the resilient
material
material.
resilient.
Yeah.
Yeah, yeah, yeah. So, foam bitumen, when you put at a very high temperature and with water, it sort of vaporizes. And it's a bit of a violent reaction, what air and all those things. So it make a foam, like, together foam and bubble up a lot, like a foam. So because it's violent reaction, water and bitumen and air all get mixed up very quickly. And then that bubbles collapse on the aggregate. So there's actually collapse time. How much is the decay time or something they call it? Bubbles collapse onto the aggregate. So that is actually carefully controlled by mixing in the correct proportions. So of course, although they are not mixing under this violent reaction, they at high temperature you can make it to do this. But of course, emulsion is primarily mixing things which are not mixable, right? You can mix oil with water, and if you start rotating it too fast. So that's a so-called mix emulsion concept, but it is happening here as a violent reaction at high temperature. So the other one, Yakapalama, so basically, it has actually, because the forces that are acting on the uh, system is from the upstream towards um, towards the downstream side. So you would have expected it to move forward. So your question is why it has tilted the other direction, right, Samanmal?
Yes.
So I think I did the analysis on this myself on a back of the envelope analysis. So now I'm trying to remember. Because this large amount of debris that has generated or collected in the front, and the restraint that you have from the bridge on the top. So basically, it has tilted. When it tilt, it can only go in that direction under restrained conditions from the bridge, because bridge is a steel bridge. Under restrained conditions, under this force system which is active from the upstream, it can only do tilting in that direction because it's a rotational moment. Under that rotational moment, that rotational force only creates is tilting in that direction. So that's what I found, how it can, under that force system, it's only allowed to go tilt in that direction.
Okay. Yep.
Yeah.
Thank you.
It's interesting.
Yeah, it's really interesting. And so in future, I mean, hope that we may not get that type of floods, but we may need to consider that factor in such as a way of avoiding water flows. Normally, I mean, we put a nose on the direction of opposite. I mean, against water flow, to where the water can go away from the piers, but still that has happened.
Yeah, but the thing is this, I told you in 2019 48 slide, I couldn't get the picture in quickly because I saw that picture by some video YouTuber, but I couldn't
Okay.
get it because I couldn't find it. But he showed in his YouTube video, 1948, they have taken a picture of this bridge. Bridge is gone. Only the three pillars are there. Those pillars are perfect. They are still the same pillars. They haven't tilted
Oh,
at all. So
okay.
water cannot do it. What has done it this time is the debris.
Okay.
Large amount of debris created the water force over a very 5 times bigger area to come onto this column, right? Why did other columns didn't tilt? There was no debris like that.
Yeah.
So debris flow with the floods is a very important thing to consider, which can block certain things, certain drainage paths, and divert the flood to some other areas and things like that. So in this instance, debris flow created a much larger force than water can provide into the bridge pillar.
Oh, right. Okay. Yeah. I thought could have because of the erosion around the pier, because it's
Yeah,
open, therefore
uh,
it has been tilt.
no, erosion sort of helped. Erosion helped because there were some blocks were removed and then or something like that. But
Yeah, yeah,
my interpretation is that
yeah.
this
Because
force
of.
is because the force is very large.
Oh, right. Okay.
That under that force system, then only you
Yeah.
can see this mechanism. It tilted in this fashion.
Yeah.
Under that force
Right,
system.
right. Okay.
Right. Otherwise, it should have actually gone to the front, right?
Yeah, that's right. Yeah. Okay, sir. Thank you.
Okay, thank you for the thank you.
I think very much informative and very efficient, very successful lecture we are finishing. So thank you so much. And shall I call Engineer Madhusank, Chair, Civil Engineers Sectional Committee, to do the formal vote of thanks?
Madam, excuse me. Yeah, madam, good evening.
Good
There is a
evening.
question in the chat box.
There's a
Am
question.
I
Okay.
audible?
What is this question? I can't see. Only the crack, this asphalt pavement cracking due to expansive soil. I think we answered that, right?
Okay, sir. Thank you very much.
We answered that.
Okay, done.
Okay.
Yeah.
Okay. Thank you very much, madam. Good evening, everyone. Actually, we just concluded insightful and for Sri Lanka frontier in geotechnical engineering and climate resilience and digitalization, which is organized by Civil Engineering Sectional Committee. Actually, Civil Engineering Sectional Committee is in the future as well. We are committed to empowering our engineers and supporting lifelong learning within the engineering community. We will organize such insightful lectures in future as well. And heartfelt gratitude on behalf of Civil Engineering Section Committee who joined this webinar, and to our esteemed resource person, Engineer Professor Jayantha Kodikara. Sir, thank you very much for sharing your valuable knowledge and expertise with us today. Your generosity and conducting this truly truly commendable, and we greatly appreciate the time and effort you have dedicated to making this session a very success. I have seen some esteemed participants as well as Professor Kulatilaka as well, my lecturer. Actually, also I would like to my special thanks to our engineer, Mrs. Kamala Gunawardana, who has given best commitment with my one request to organize this session. She has connected Professor Kodikara for making this event possible. Also, thank our members who joined here online and your inputs in bringing this event success. Your enthusiasm and active engagement with the interaction made this session meaningful. Thank you very much. And the secretarial staff of ISL, city manager Chamila, and the technical support. Thank everyone. If I miss more such enriching sessions in the future, and keep connected with us. Thank you very much. Good evening, all. Thank you.
Thank
Yeah,
you.
we'll formally wind up
Thank
the
you.
session. Thank you.
Thank
Thank
you.
you.
Bye-bye.
Thank you.
Bye.
Bye.
Thank you.
Bye. Thank you. Thank you, Andrade. Bye.
Thank you. Oh, thank you, Kamala.